Okay, yeah, thanks for the opportunity to give a little bit of an introduction into the work that we're doing here at the DFKI in Bremen and the area of underwater robotics based on artificial intelligence tools and methodologies that we're using in order to make them more efficient and more usable, in fact, in this very challenging domain. But before I start, I would actually like to give some thoughts on this program. I think really it's a great program. I think this is the second time we are part of this such a program in the underwater area of underwater robotics and AI. And it has been a great opportunity, I have to say. I mean, based on the people that have been applying and that were coming to our labs and institutes, I really had a wonderful impression of the motivation, the background, and the dedication with which these people are pursuing this research. And for me as a teacher, it's it's really very pleasant experience, you know, to be able to work with people like you. So thank you for that, first of all. And having said that, I would like to go into my a little bit of an introductory talk here. So the DFKI actually. It's the Robotics Innovation Center, which is part of the German Research Center for Artificial Intelligence. And you can see in this little map up there, it's actually a center that is distributed over Germany. Today we have 5 locations. Actually, the 2 oldest locations are in Saarbrücken and Kaiserslautern, down in the southwest of Germany, which has been funded actually in the 80s. So in 1982, 83, the German government decided to start a competition for a national center on artificial intelligence, which I think is remarkable because that was in a time when artificial intelligence actually had already seen what we call AI summers. You know, when AI was in not everybody's mind and everybody's mouth as it is today, but it definitely hasn't been an area of research. Somebody is typing on his keyboard, and that's quite loud. So maybe you can just close your mics. It's maybe easier for all of us. Thanks. So that was in a time when artificial intelligence was already popular, but a very different type actually of artificial intelligence, what we call today symbolic AI, based on planning, reasoning approaches, rule-based deduction systems, and so forth. Expert systems was a big challenge at that time, and that was when the DFKI actually was initiated, so over 30 years ago. And then Bremen actually was the second, the next step, the third center that came to the family of research institutions in 2006, actually. So many years later, more than 20 years later. The former director of the DFKI, Mr. Walster, approached us here in Bremen. I was just coming back from the United States. I worked my first professorship in Boston, the Northeastern University in Boston, and we went back to Germany and started the chair of robotics at the University of Bremen. And then the former director said, okay, we need to make the next steps in artificial intelligence research, and that includes robotics, which means that it includes physical systems. So it was a change, you know, when people started to realize more the need actually for studying artificial intelligence, not just in the form of computer programs and simulations, but actually making the step into the real world by incorporating robotic systems, which by definition have to interact with the real environment. So that's the beginning in 2006. Now, at this point today, we have over 130 researchers working in the area of robotics, from very basic mechanical engineering. So all the robots that you see here, they are basically built in our lab by ourselves. So we have mechanical engineering, we have electrical engineering, of course, creating the tools and the equipment that we need to control these systems. And of course, then we move forward into the actual control of the kinematics and of the other components of these robots, all the way up to the high-level planning and other AI-based technologies and methods that we need to have systems that are in some way useful. And one big goal when I came back from the United States to start the lab here on robotics was actually to look into long-term autonomy, systems that would be interacting with a real-world environment over extended periods of time. Extended periods of time is not, an hour or 2 hours or 3 hours. It's not even a day or a week. It's something that can stretch over months and maybe even years. And there's two disciplines in robotics and artificial intelligence where this is really a key ingredient, and this is in the underwater area, but it's also, and maybe even more so, in the area of space robotics. So space robotics and underwater robotics, that were the two funding starting areas of application that we tackled here in Bremen when we ventured into this new endeavor. And as I already said, it's important to understand that robotics is really, and especially artificial intelligence-based robotics, is really an interdisciplinary adventure, if you want. And that can be seen also if you look in our institute, in the areas and the disciplines that people are coming from. It's computer science, of course, like maybe it's hard to say. I don't have the exact numbers, but I would guess that we are probably 70–80% of the people are actually or having a computer science background. But there's a big group of people coming from engineering, both mechanical engineering and electrical engineering. There is biology, neurobiology. There's a lot of people coming with a background of mathematics and also physics. Later I may be talking about a little bit about quantum computing. So there's a lot of physics physicists that are joining us from all kinds of motivations and interests. And this combination of disciplines in our institute, sitting really side by side, door by door, is really something that I think is a key ingredient to tackle the problem of artificial intelligence in robotics. So this is the little bit of history. So I already talked a little bit about the DFKI in general. And actually the DFKI is not the kind of institute that you might know from, especially from Germany. If you think of Germany, maybe you think of the Fraunhofer Gesellschaft, maybe you think of the Max Planck Gesellschaft, maybe you think of Helmholtz Society and so forth. And these are all big research institutions, actually families of institutions that have a very solid and quite a big amount of basic level funding from the government. But the DFKI is not that kind. It's actually a public-private partnership. So we have been, when then the government started this institute in the 80s, they said, okay, we want to have industry on board, and that's what's depicted here in this picture. Actually, the DFKI is a joint venture. It's a not-for-profit organization that is in the majority, shareholders are coming from industry. You see Airbus, you see BMW, Bosch, Claas, Daimler. You see also SAP, for example, Microsoft, and Google and others. They're all part of the board of the DFKI, and of course the key members or the states of Bremen, in which the locations of the DFKI are located. They are also part of the board of the DFKI, and of course the federal government is part of the board of the DFKI, and that's quite a unique setup for a research institution, that we have this combination of industry and public partners that form together this institute. There's two flags that you can see. It's Schleswig-Holstein and Hessen. This is two more countries or two more states of Germany which are currently in the process to become members of the DFKI. So this is also another aspect of the DFKI, and the history of the DFKI is that since the 80s it has been growing in a quite interesting pace, so there's more and more states in Germany that are coming and joining us and establishing research institutions. Hessen, for example, the University of Darmstadt will be joining us with a very strong group in machine learning, in data-driven machine learning approaches, deep neural networks, and that kind of stuff. So that's a very interesting, unique environment. One thing that I have to say, even if there's all these companies here in the shareholder group, the motivation for those companies to be shareholders is not in the classical way that you would think of shareholders, to invest in a company in order to make a lot of money. This is not the case. These companies are not making any money at all. They actually have to provide and provide research funding. So the reason they joined the DFKI is not for revenue. At least not monetary revenue. It's more in terms of revenue in knowledge, in human resources. So many of our students, many of our people are finally, going to those companies, having jobs in these companies after they finish the time at the DFKI. So that was a little bit more the formal stuff on what the DFKI is and why we are here and where we want to go. If we look into artificial intelligence, I think it's a major aspect to understand that artificial intelligence, if you really look at it, never has been an isolated field of research. So actually this graphic shows it, that artificial intelligence basically sits at the heart of computer science. That's my old professor. He always said that computer science, actually the core of computer science is artificial intelligence, and we can talk on the next slide why that might be really true. And computer science, in fact, is already and has always been a bridge between the engineering world and the science world. So the engineering coming with mechatronics, so the combination of physical artifacts, that have to be controlled, that have to perform certain tasks in real world environments. And in order to perform this, and the more structure we gave to those machines, to those artifacts, the more degrees of freedom, the more sensors we added to those systems. Of course, the need for computer science became harder and harder, and it became more difficult, to fulfill these needs. So if you have systems that have to interact with an environment in extended periods of time in some intelligent way, then of course the need that you put on the control part, on the computer science part in these machines is becoming stronger and stronger. And that's why computer science very early, of course, also looked into the field of science, the natural science. One very prominent part, of course, is the part of natural science that deals with the understanding of cognitive processes in human beings and in biological beings. But we should not forget that a big deal for the existence of computer science in the way we know it today is actually linguistics. The Chomsky hierarchy of formal languages gave and laid the foundations for all programming languages that we have today. So all of these languages are going back to this hierarchy of formal languages that has been introduced by a linguist, Noam Chomsky. And of course, another area, and that's much also for my own private motivation to study artificial intelligence at the University of Bonn. I studied computer science, and as a second matter, you could choose between mathematics, you could choose between economics. It was very popular at the time, and I chose neuroscience. I studied computer science and neuroscience because one key aspect, of course, for artificial intelligence is that we have no clear definition of what intelligence actually is, not to speak about what artificial intelligence actually is. And therefore, it made a lot of sense for me as a young student, to look into the only existence proof that we have for whatever level of intelligent beings there might be, and that's what we see in biology, in neuroscience. So there is this very strong link between those two areas, and I think actually, if you look at it, if you study artificial intelligence in the area of robotics, actually this is where it all comes together, where you have to integrate all these aspects. You have to come up with very solid mechanical systems with very solid artifacts, that are able to survive the interaction with the real world. But on the other hand, you also have to deal with very, very high level metaphorical sometimes issues like what is cognition, how can we implement it, what would be the perfect architectures, to come up with these aspects that we know from natural sciences. So to say this in advance, that artificial intelligence really is at the core of engineering and natural science. And the reason I said that is because if you look at the beginnings of computer science, actually, obviously, Alan Turing is the person that has to be mentioned here. And in his paper, actually, in Intelligent Machinery from 1948, he was already thinking about these issues and establishing the I think key idea that's still driving me, at least today, that he said that if we want to study artificial intelligence, what we actually have to do is we have to create artifacts that interact with a real world environment over extended periods of time, and that have to learn from it, that have to learn from the interaction, and from learning from the interaction with the real environment, they can steadily and in an iterative process, improve their level of intelligence to become something that we might want to be able to call artificially intelligent. So having said that, or having heard that from one of the greatest mathematicians of the 20th century, which Alan Turing by all means was, we have to realize that there is no analytical way to tell us what is artificial intelligence first, and then there's no analytical way that tells us how to solve it. So there's nothing in mathematics, in pure mathematics as we know it, that can give us the solution for artificial intelligence. Okay, so and that is not what I'm saying. That's what a person like Alan Turing has realized already in the very early beginnings, just after he basically laid the foundation for what computer science is. So the Turing machine is still the machine that defines the capabilities of all the computers that we have, no matter how fast, no matter how big, no matter how fancy, they are all Turing machines. And we will never be able to go beyond what a Turing machine can compute. So, and that's something that we have to keep in mind. So if we move forward, and this is what Alan Turing did in his reasoning, in his Gedankenexperimente, as he himself called it, we have to realize that we need to go on a more systematic way in terms of thinking in architectures of computer control programs and so forth that can sort of emerge to become something that resembles intelligence in the way we understand it. And and he himself, actually, when he wrote this paper in the 40s, he realized, okay, so this is theory. This is what I think we should do. But if I look at what we can do in the 40s of the last centuries, he said that, well, we will never be able today, to build robots that would even come close to what I require from them. So if you look at the electric motors that we had at those times, if you look at the sensors that we had in those times, if you look at the not existing computing technology, the transistor hasn't even been developed, that they had in these times, there was no way to build robots that would fulfill the requirements that Alan Turing put up, to say, okay, and this is a mechanism, this is an artifact that I could actually use in order to study artificial intelligence in the way I proposed it, by having extended real world interaction and learning from it. So, and that's why basically in the same paper, he said, okay, so we should abstain for some time from this path and go on another path, which actually looks at things like game playing, natural language understanding, translation of text and so forth, cryptology, and of course, very important, mathematics, logic, and reasoning. And therefore, I think many people say that artificial intelligence was coined and based and founded in the 50s in the famous Dartmouth conference. I think if you look at this paper, actually Turing laid the foundation for what became the standard in artificial intelligence for the next 40, 50, 60 years already in this paper. The point was that he didn't coin the term artificial intelligence. That term was actually coined in this 56 Dartmouth conference, but the path, the field was actually leveled and set already by Alan Turing in this 48 paper. Okay, and then I think another very interesting aspect to look at is, why was this thinking actually coming along? It's because just after the Second World War, 48, people were gathering. Here's a group of scientists, actually this year is Alan Turing, in very interdisciplinary teams, in very interdisciplinary groups for very, very simple and if you might call them trivial reasons. They grouped in what they call dining clubs. And that was because science was in this time actually a field of trying to make a living that wasn't very, always feeding yourself, So some of the researchers actually had so little money that even also in England after the Second World War, people needed to find a way to get food, So dining clubs were the clubs that have been initiated by some wealthy people, funding, people coming together and having a dinner, sitting together and eat. And that was great because it brought together very different kinds of people. So this is a nice example here. One of the guys here also in this team is the guy here in the middle, in the back. That's Gray Walter. And he came up with the first robot, actually. And this is the turtle robot. I don't have the time to look into this, but it's a very simple robot based on 2 valve systems, actually, that show the behavior that if you look at your lawn mowing robot, or if you look at your carpet cleaning robot in your office or in your apartment, it's actually exactly what this turtle robot was doing. It was driving around, basically. Without a plan, without knowing where to go, why to go there. But it was just driving around, exploring the environment. And whenever the battery in this robot went to a certain threshold, down to a certain threshold, the robot had a mechanism to go into a nest. That's what he called it. Gray Walter called it a nest, which was basically a little hut, that attracted the robot with a light sensor. And it was driving into this nest, and then it was recharging itself automatically. And as soon as the battery level came back to a certain threshold, the robot would try to avoid the light. And so it went out of the garage and that was going again in circles around in the environment. So that was in the 50s. A robot developed by this little guy here in the back with the glasses, Gray Walter. And Gray Walter himself was actually an EEG researcher. He wasn't a roboticist. He got the idea of doing this, of looking into these aspects, because he was assembling in these groups, in these interdisciplinary groups at the diner clubs. Actually, for the 100th birthday of Alan Turing, there was a famous person from MIT who gave a laudatio speech, and this guy actually looked into this history of these dining clubs, and he found out that in fact the bill for the food was always lower than the bill for the drinks. So it looked that these guys also had a lot of drinks when they were talking about science. So here's a little bit of some pictures. You know, this is the little turtle bot here. The thing there up in the back is the hut. And the robot, basically, this is how they did videos in the 40s. You know, they were just taking a snapshot with a very long exposure time, and then you can see the light traces, which is the path that the robot followed. And here's the path that leads the robot into his charging station, and then basically, as I said, coming out and doing his thing again. So basically, what Turing came up with is what's depicted in this little graphics here. It's the robot problem. You know, you have the robot on the one hand, on the left side, and this robot, you know, there are certain requirements for this robot. It's not just you know, a tin can on wheels. No, it has to be a system that is kinematically able, you know, to deal with a natural environment. So this is actually in his paper. He says let the robot roam the English countryside. So that's why I try to depict a picture of the English countryside here. So this is the environment in which this robot needs to be wandering around, making all kinds of experiences with this environment and learning from it. So this is the learning problem that we just depicted here. So the robot perceives the states of the environment via his sensors that is equipped all around the robot, hopefully many different sensors with different modalities. And what he needs to do is he needs to find an action in order to interact with this environment in a useful, senseful way. And ever so often, there is a signal coming from this environment that tells the robot whether this interaction was good or bad in terms of the overall goal of the robot. So what we want to understand to solve the problem is basically just to find this function f, you know, that maps from states to actions. That's all. This is the simple function that we need to solve. And when we solve that, we will be happy and we solve the artificial intelligence problem. However, this is a long endeavor and we have no, as I said, direct analytical way. So what we have to do is we have to work with expectations. And that's one approach here. So basically, in the learning approach, we work with expectations about the development of the long-term expected rewards, this little red signal that's coming from the environment over extended periods of time, in fact, in theory, over infinite periods of time. And based on those expectations, we can form a function that tells us something about the utility of doing and performing a specific action in a specific state. And that's, of course, an approximation of that utility because as we know, we have to do it infinitely often in order to actually come up with the true value of this function. But once we have this value, once we have a slight idea about how useful it might be, you know, to perform a specific action in a specific state, then based on that, we can develop what we call policies by looking at ways to find all ways to maximize this long-term average expected reward by choosing the best possible action in a given state. However, that's, even though this is a rather simple definition of the basically robot control problem, it's still a problem that we are struggling with to solve and that we are, you know, looking into in various ways in many different applications, and underwater is one of them. So there's basically, if we want to come up with these kind of systems, whether that's in underwater, space, or wherever, we have four major challenges that we need to tackle. And one major challenge, and the most important and in many ways often neglected part of this problem, is structural complexity. And what I mean by structural complexity is actually what Alan Turing already asked us to do, is, you know, to come up with robots that have the kinematic disposition to interact with an environment in a non-trivial way. So if you have a very, very simple robot, like I always call them tin cans on wheels. You have this trash can with two wheels underneath, and it's just driving around in a flat surface. That's not the kind of robot that I'm talking about. That's not the kind of robot that Alan Turing had in mind when he was thinking about long-term interaction and learning from it, because you can only learn so much. However, if you have a robot like the one that you see here in this video, this robot has so much kinematic disposition for interaction with the environment that, in fact, it becomes an algorithmic challenge, for us to control the system. And that's why we have, and that's the next challenge, we have to find ways on how to deal with this algorithmic complexity. And you should think about it. If you just add one more degree of freedom to your robot, in general terms, basically, you're doubling the amount of algorithmic complexity. So it's an exponential rise of complexity with every added degree of freedom in a very general and broad way. And that's the key challenge. So on the one hand, we need these very complex mechanisms, but on the other hand, we are very poorly, positioned to deal with the complexity that comes with the rising structural complexity, to deal with the algorithmic complexity that comes with the rising and increasing structural complexity. And that's something that we have to deal with. That's why it's very useful and sensible to think about architectures, for example, and also why it does make sense to think about learning, because we're coming to the borders of where we can solve some of the problems that the structural complexity confronts us with in the classical sense, in the way we learned at school, how to solve the inverse kinematics or direct kinematics of a given kinematic chain. So that's all fine and great, to solve these differential equations when you talk about kinematic chains, that have maybe 5 or 6 or maybe 7 degrees of freedom. But if you go beyond 7, 8, 9 degrees of freedom, if you go into connected kinematic chains, so like you showed in this video here, there you have the robot actually forming a circular connected chain by grabbing the parcel here in the middle. If you have those closed kinematic chains, if you have parallel kinematics, if you have parallel kinematics in combination with closed kinematic chains, and if you have all this stuff together in the robot that you see here, then the way we can classically solve the problem, the control problem, is just no longer valid to us. It's no longer available to us because it's too faulty, and sometimes even doesn't really come up with a solution at all. And there is the first entry points for learning in my approach is where we can use machine learning architectures, machine learning approaches, but also hybrid approaches to tackle this problem of dealing with the complexity. And then once we did that to a certain extent, we can actually take this robot and bring it into a real world, into a real environment. This is just a picture here from a commercially available robot in a factory setting. And from all experiences that we have, once we bring our laboratory robots into a real world, it will probably survive 10 minutes. And after 10 minutes, you see all the problems that you have in your robot. You see all the problems on your control side. You see all the problems on your mechanical side, on your electronic side, and of course, you also see all the problems that come with integrating all these components into one system that then has to survive the unforgiving nature of real-world environments. And that means, and that's not bad, but what it means is that we have to go back to the lab. So we created something, we put it into a real-world environment, we see that there are so many problems, so we have to bring it back to the lab and we have to start over again, maybe because we see that we need another degree of freedom, or that we need another sensor modality or something like that. And basically what you could think of is the circle is closing. We're going back to start. However, this is not really true, because fortunately we are not living in a two-dimensional world, we're living in a three-dimensional world. And that means when we close the circuit, when we bring our robot into a real-world environment and we see all the problems that it has, we are going back to the lab, but on the next level. We have already reached another degree of understanding. We have already reached another degree of being able to cope with complexity and so forth. And therefore, you can think of it not as a circle, always, going in a circle. No, you can think of it as a spiral, that brings us upwards towards actually systems that are capable to survive the interaction with the real world while at the same time doing something useful. So these are the four major challenges in my world, the way I see it, and that we have to solve. And you can spend your whole career, doing this. There's no way, and even more than just one career. Okay, so for the RIC, for the Robotics Innovation Center, we've set this goal, and here's a few of the application areas that we work on. So there's space programs that we're working on, basically coming up with complex mechanisms for exploration of other planets, terrestrial exploration. Then, of course, the other big field is underwater robotics. We'll be talking about this for the rest of the talk, but also things like logistics, production, search and rescue robots, so robots that can navigate in unplanned, unstructured, maybe harmful environments. Another very, very big field of research and something that I'm really very interested in is exoskeletons for assistance, but especially also for rehabilitation. So there's a big team in my institute that's dealing with exoskeletons for rehabilitation of stroke patients and also of spinal cord lesions. Very, very interesting field and also very useful field. Yeah. But we don't have the time to talk about this. And then there's electric mobility. We've also been, venturing into the area of how would we build a car if we were allowed to do so, and because we are roboticists, the car that you see in this picture is what we actually came up with. But again, this is subject to another talk. So in the underwater area, I think it's several parts that are really interesting for us, and one of course is underwater navigation. So we all know navigation, probabilistic navigation approaches, the SLAM approaches from the terrestrial world. There's very early work that we did in the 90s already for probabilistic navigation. And that's one aspect that we're dealing with here in the upper left picture, is to be able to navigate in an unknown underwater environment with a system. Actually, in this case, in the upper left picture, a system that is just floating in the water column. We then, in the lower left side here, we brought this into an application where we build a system that's called the Flatfish that is supposed to be subsea resident. So very much of the thing that I just showed you with the turtle robot, here it's the same idea, actually. We have this little hut here underwater, though, on the bottom of the sea. And in this little garage, this actually it's not so little, it's a big garage. The robot is positioned, and then it will be going out from this garage on his mission plan, following, for example, the pipe. And you can see in the small picture inside the video, that's the real world video, and the rest, of course, is an animation because we don't have the possibility to follow this robot underwater. And this is what the system is doing. It's basically staying underwater for all time, and then being set up to go on mostly autonomous missions, avoiding obstacles and stuff like that, and then maneuvering back to his target. One thing that we can think of, actually, that's something, if we talk to the underwater guys, is that they say, okay, this is really great because there's so much infrastructure that we have on the bottom of the sea, especially in the area of oil and gas, that we haven't seen for 30 years, you know, because 30 years ago, when we dropped this stuff in the water, we know it was there and we knew it was working, but ever since we couldn't have a look at it because it's at 5,000 meters water depth or something like that. So there's no way we can actually go there. With these underwater systems, we can actually go there. We can take the sensors that the system has, come up with three-dimensional reconstructions of the infrastructure, and these three-dimensional reconstructions can then be inspected and monitored by operators on the surface, and they can take care of it and say, okay, there's need for repairs or not. And the basic idea, I'm still in the lower left video, is then the robot basically goes back to his garage, docks into the garage. Then, of course, we have the possibility to transmit data. Then the data can be transmitted to some onshore operations center or something where the data can be analyzed, and then, you know, new missions and something can be planned. And that's all about navigation. But then, of course, if we come to the right side of the videos here, we also have to think of other things, because just swimming in the water column is nice, and observing what's going on is also nice. But in many cases, we actually want to intervene. We want to manipulate stuff. And that's what we see here in the lower right side video. Is a robot actually that is driving on the bottom of the seafloor, and has an underwater manipulator arm. This guy here that you see here, the arm also has been developed in our institute from the mechanical electrical engineers, and it's able to operate up to 6,000 meter water depth, and to operate things like you know, turning a handle or stuff like that. So intervention is the next big challenge in autonomous intervention, the next big challenge in underwater. And then if you go up one video here, the video here, you see actually two systems, and the long torpedo-shaped system is actually docking to another system. So that is robot teams interacting in the underwater area for whatever mission plan they have. You know, for example, the one robot has been picking up a sample or something, and the other robot comes and takes the sample, docks to the robot, takes the sample, and brings the sample back to some other station where it's then further analyzed. And this is what we've been able to show here. I think first time that I know that this has been done, where two robots in the underwater area are actually having what they call a rendezvous and docking in space maneuver, right? So I think the next slide here, I think it's coming up, is actually the next video here. That's something that I wanted to show you. Here's the lower right side is another system that has just been completed. We call it the cuttlefish robot. And that's actually a robot that is swimming in the water column, but it has two manipulators attached to it under its belly, basically. And it can change its position, as you've seen, to a vertical position in order to use the manipulators for manipulation, and that's the simulation. And here is the real-world image of that. That's taken in our tank at the University of Bremen, or at the DFKI in Bremen, in our big underwater tank, where we can do these kind of experiments and testing and real-world hardening of the algorithms and the complexity. And handling the complexity. So this is another step towards, you know, actually being able to handle the underwater environment on many levels, different levels, including manipulation as well. Not just navigation, but also manipulation. So for the students in the audience, I think I would like to show you a little bit about the infrastructure that we have here at the Institute. So there's on the left side, you see many different robots that we have, but there's also an interesting aspect is we have two test sites. One is the in-house test site in the lower level, lower right video. This is the big underwater test basin where we can install, you know, pipes and stuff like that in order to train the systems to detect the pipes. But then we also have a real-world test environment on the island of Heligoland. Sorry, I've been moving forward too fast. This is up here, the upper right video. This is actually an island about, I don't know, 30, 50 kilometers off the coast of Germany, where we have an outdoor environment. We have also some lab spaces there, so we can stay there for a week or 2 weeks and take the robots, bring them into this real world environment, do some testing, and then analyze or repair the robots if they're needed in our lab space. So that's very useful to actually make the step from the laboratory environment into a real world environment. Finally, I would like to show you a few things based on the combination of space and underwater. So in different programs, basically funded from the German Space Agency, which is now looking into, and the European Space Agency as well, looking into ways to, have missions to moons, icy moons, ice moons around Jupiter or Saturn, Europa, and Enceladus. These are moons basically covered by a huge, thick layer of ice. And underneath the ice, we know now that there's an ocean of water, liquid water, up to 10,000 meters deep, actually, so much deeper than sometimes we see it on Earth. Fortunately, the moon is very small, so the pressure is relatively low compared to what we find on Earth. And the challenge, of course, is to have systems that will be able to penetrate the ice surface. And once they've penetrated the surface, we also need to be able to explore the environment, because in fact what people think is that because the cores of these moons are actually hot, they are melting hot, like the Earth's core itself, melted stone material, there might be what we call black smokers. So that's what depicted here in the upper left video. This is basically little volcanoes in the deep water environment in the bottom of the ocean in Pacific and so forth, where basically material comes out that is very high in not nutrients but in chemical elements that actually we know organisms can live off, even though there's absolutely no sunshine. So they have a way of using the chemical interaction with these materials that are coming out of those black smokers to live. And of course, the idea is that even on these icy moons around Jupiter, for example, there might be such organisms as well. So we need to have these robots that are capable to first penetrate the ice, which is sometimes up to 10, 20 kilometers. That's a huge, very big ice layer. But then we have the liquid ocean, and then we need the underwater robots. We need stuff that we are working on here on Earth. So yeah, and I think this is, I hope I didn't spend too much time, and that's the end of my talk. Thank you for your time.
Yeah, thank you very much. It was quite an interesting talk.
50 minutes.
Providing a bit of perspectives, but yeah, I think we can maybe open the floor a bit for some questions if anyone of the audience would like to ask something. I see a question in the chat. And researchers in DFKI about wireless communication for underwater. Maybe I could answer this question briefly. So from the videos that you saw, like with the docking, the communication is basically, once we are in a very close range, just the classical wireless Wi-Fi connection works, like within, I don't know, 1 to 2 centimeters if you have like the antenna separated. Of course, if you are a bit further away, up to like a couple of meters, there's like some light communication, but this is basically just based off like some off-the-shelf components, and further than this, then it's more acoustic communication, of course.
Yeah, but the absence of the possibility to communicate, of course, at the same time raises the need for autonomy in the systems, because classically you don't have a real good communication channel to your system if it's in the water column.
Yeah, of course. I mean, acoustic is like very low on bandwidth and like has lots of dropouts, of course, based on the line of sight.
Mm-hmm. Okay, so thank you.